Good morning. Today we are getting more technical with the sensors. In the data acquisition software, we have two fields that help us to transfer this voltage signal from the sensor into a physical quantity. In our example, the accelerometer outputs a voltage signal. This signal is multiplied by 10 to obtain G, and it also has a zero offset. Today we are going to find out where to get the scale factor and the offset. This is true for any data acquisition software, not just ours. For any sensor, the data can be found in its data sheet. So for this accelerometer, this model number, we can find the sensitivity or the scale factor here. So for it's 100 millivolts per G, or 0.1 volts per G, which is transferred to 10 G per volt. This is the source for the 10 which we used before. For the piezoelectric sensors, there is no bias. They are not good for any constant value. They only work in dynamic range. So there is no bias. So you are using this scale factor with your setup. Fun fact, when it's written like this, millivolt per quantity, it's called sensitivity, and when it's written like this, it's called scale factor. A quick side note before we continue. High quality lab equipment like this sensor, they all have individual serial numbers, and they are calibrated individually at the factory. So as a consequence, each sensor will have slightly different sensitivity value than the datasheet value. So it depends on how precise you want to be with your setup. You can use either this or this. The choice is yours. Now, what about this? This is our displacement sensor. We can also find its datasheet. Sometimes you need to work a little bit to get the scale factor. So we have the measuring distance. This is the full scale. It measures from 100 to 600 millimeters. And the output signal is from 0 to 10 volts. What we can do, we can go 600 minus 100 divided by 10, which means it will be 50 millimeters per volt. So this is really 6th grade math. Now let's see what we can do about this unit. You remember this is a directional accelerometer, and this is it's a cheap unit, so the datasheet looks accordingly. We'll start here. This is sensitivity, and it's given as a minimum, typical, and maximum values because they cannot be defined precisely. So let's use one of those. We'll do the typical value of 300. And additional thing that you can find here is the bias level at 0G. So at 0G, the typical value is 1.5 volts. And to use the sensitivity, we are starting with 300 millivolts per G, which is the same as 0.3 volts per G, which is the same as 10 over 3 G per volt. But we also have the bias. So the conversion goes like this. We have the voltage from the sensor with the bias. All this is multiplied by the sensitivity, by the scale factor, sorry. This will be volt. This will be already in G, and plus 5 volts, which will be the bias. So you are putting this as the scale factor in the software and this as the bias. And you want to put it with the negative sign for the software to nullify this value because it has no physical meaning. After you got your scaling factor, it's a good idea to check if you are correct. The way to do it is to compare the value, the output value in the software from your sensor to the actual value that the sensor sees. Here I have this tiny accelerometer, a very simple one, and I connected only the z-axis. Z-axis is vertical in this direction. So the cool thing about this sensor in particular is that it can see constant accelerations. So in this configuration it should show us 1g. Let's see if it happens. So we play. You can see that this is 1g, this is the line of the output of the accelerometer. So the way to check if you are correct with the scaling factor is to play with it a little bit. So if we have our vertical acceleration, in this configuration the sensors should show us around 0. As you can see here, it really falls down to 0. And if you flip it, it should go to -1. So you see we are slightly off, but this is because that the data for this unit has some discrepancy, as you saw in the data sheets. Let's go back. This is 1, 0, and -1. So you can do this for any sensor that you use, and it's a good idea to do so. Obviously, you cannot apply, cannot check this with every sensor that you have, but the ones that you do, it's a good idea to verify your data. Next, let's talk about what happens when you connect your sensor to the data acquisition hardware. We'll do the example of our accelerometer, which has a measurement range of 50G, which is translated to the full scale of 5 volts. In the data acquisition, let's say your measurement range is 10 volts, and your A to D resolution is 10 bits. A to D stands for analog to digital resolution. And the meaning of 10 bits is that your measurement range is divided into 2 to the power of 10 discrete values. So in your measurement range, you get smooth continuous values from your sensor, but in the instrument, this is divided by 1024 values. So you have a little jumps along the measurement range. So if you have low resolution instrument like this, it makes sense to adjust your measurement range to the full scale output of your sensor. So if you are using instrument with 10 bits of A to D resolution, it makes sense to adjust the measurement range to 5 volts. It also makes sense to do this mindfully. So, for example, if you are using this sensor, but you are only measuring 10 Gs, which translate to full output of 1 volt, you will want to adjust this measurement range to 1 volt. In order for this to be divided by 1024 discrete values, so you'll get smoother recording. So, of course, this is very, very low resolution. Modern instruments have 16 bits of resolution or 24. With 16 bits, you are getting 65,000 discrete values with your full range, and with 24 you're getting more than more than 16 million discrete values throughout your range. So this mindfulness of adjusting the measurement range is only relevant when you are using outdated hardware. With the modern hardware, it hardly makes any difference. So that was my take about sensors and A2D resolution. Let's talk about the final bullets to remember while using this instrument. First of all, each side, so we have this side and the other side, has 8 channel connectors. The channel go wherever we have channel high and low with the number. So high will go the positive from the sensor and low will get the negative from the sensor. Channels are numbered from 0 to 7 on this side and from 8 to 15 on the other side. One important thing to remember is to always connect your sensor to the active channel. If you activate channel in the software, please connect the sensor to the inputs. Otherwise, your setup will get junk from the non-connected points. And one last thing is choose one of your active channels and connect resistor between the channel low and the ground of the instrument. The ground is here. This will ensure that the ground of the entire acquisition setup will be maintained throughout the test.